Welcome to our YouTube channel. This is Ernest coming to you from MATLAB Tutorials in Toronto, Canada. Our mission impossible, as always, is simply to convert some of that hate energy to love energy. Of course, that energy I'm talking about is the hatred that a lot of people have for mathematics, which is certainly unfortunate. Hopefully you can learn to love the subject because it really is a beautiful subject. As your screen indicates, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. This is video 3 of a continuing series on exponent laws. And so this is just a continuation from video 2 on exponents. And part C over here concerns the power of a power law for exponents. So power of a power law goes like this. If you have a set of brackets and you have a to the power b inside the brackets, that's a power in and of itself because a is the base, c is the exponent, but then the entire power is raised to another exponent, c. Let's try to interpret this. Inside the brackets, b is the frequency for a, so inside the brackets we really have BA's inside the brackets, and then that group of BA's inside the brackets is replicated C times. So again, BA's in here is replicated C times. So the entire or the totality of A's becomes a to the power b dot c. For example, if we have a to the power 3 all to the power 2, we have 3 a's inside the brackets, and then to the power 2 means that you have 3 a's, a block of 3 a's, but twice. So you have a product of 3 a's times the product of 3 a's, you have a product of 6 a's altogether. And that's why this particular law works. So again, a to the power b all to the power c is a to the power b dot c. B is an exponent, C is an exponent, B is the inside exponent, B is the outside exponent, and of course A is the base. And we use POPL, as a shortcut for power of a power law. Let's look at some examples. Example 1, if we have bracket 2 to the power 3 all to the power 2, all we do is multiply the exponents. Of course the base is 2. We get 2 to the power 3 dot 2, which is 2 to the power 6. And that's a single power now, which evaluates to 64. Example 2, we have inside the brackets, we have 3 to the power 2 all to the power 4. So again, you multiply the exponents together, and we get 3 to the power 2 dot 4, which is 3 to the power 8. And then 3 to the power 8, you don't want to do manually. So at this point, I would go to the calculator and use the power button to crank out 3 to the power 8. When you crank it out, you get 6561. Not only does this work with integer bases, but you can use fractional bases as well. So for example, example 3, we have 2/3 all to the power 3. And then that entire bracket is all to the power 2. 3 is the inside exponent, 2 is the outside exponent. You multiply the exponents together. So altogether we have 2/3 to the power 3 dot 2, which of course becomes 2/3 to the power 6. And then if you want to, you can expand that out, but I chose not to because it doesn't really prove anything. Okay, so let's go on to the next slide. Let's look at Q1. It says evaluate using PSL plus QDL plus POPL. PSL, you recall, is the product sum law, QDL is the quotient difference law, and POPL is the power of a power law. So we're going to be using all these 3 laws simultaneously. If we look at this expression over here, we have dots in the numerator and dots in the denominator. There are no plus or minus signs anywhere as separators, so we declare this to be one cluster. And if we look at all the bases, we have a single base, and the base is 2. And we've got a slew of exponents here. But the big idea to realize is that you've got one cluster and you have a common base of 2. And we're going to use all 3 laws over here to execute the problem. So in the next line, because you only have base 2, you write down base 2. And what we're going to do is rapidly collect all the exponents for base 2. Over here, we scan the numerator first. We pick up a 2, drop it down, and then we have 3.2. That's power of a power law. And we drop it down to 6. And we have 4.3, which is 12. Drop it down. Then we have 8, but because it's on the bottom, it becomes minus 8. And then we have 2.2, which is 4. Because it's on the bottom, it becomes minus 4. So now in the exponent over here, we have a simple integer string, which is easily evaluates to 20 minus 12. 20 minus 12 is 8. So at the end, we get 2 to the power 8. And you either know that to be 256, or you can use the power button on your calculator to evaluate that. Okay, but 2 to the power 8 is 256, and that's the end of the problem. We're done. Let's go on to the next slide. Q2. So we're going to be using all 3 laws concurrently and to evaluate this expression over here. Again, we notice that we have a single cluster. So we only have to worry about one cluster. And of course, exponent laws only apply to one cluster at a time. And if we scan this cluster carefully, we notice that the common bases are 2 and 3. And we're going to use all 3 laws concurrently to simplify the expression. But we're going to consider one base at a time. So we're going to consider the lowest base, base 2, first. And whenever we consider base 2, we disregard base 3 altogether. So you pretend like it's not even there. So let's scan for base 2 exponents. Over here we pick up a 2.2, which is 4. There it is right there. And then 3.2, which is 6. There it is right there. On the bottom we get 2.4, which is 8. But because it's on the bottom, it becomes minus 8. And we're done with base 2. Now we go on to base 3. And we scan the numerator for base 3 exponents, and we get a 4.3, which is 12. Scan the denominator for base 3 exponents, we get a 2.4, which is 8. But because it's on the bottom, it becomes minus 8. So now we have a simple integer string here, simple integer string there. We evaluate the string, and we get 2 to the power 10 minus 8. Why? Because we have 10 good guys, 8 bad guys. And over here we have 12 minus 8, which is 4. So 10 minus 8 is 2. We're left with 2 to the power 2, dot 3 to the power 4. 2 to the power 2, of course, is 4, and 3 to the power 4 is 81. You should know that. And then 4.81 is certainly 324, and we're done. So this entire mess up here finally evaluates to 324. And we've done it quite rapidly. Okay, there's no need to take many steps applying these laws individually. The laws are meant to be applied simultaneously. Let's look at the next slide. Here's Q3. Again, the same 3 laws: product sum law, quotient difference law, and power of a power law. When we look at this expression over here, the first thing I notice is that there's a plus sign. That plus sign is a separator between a left cluster and a right cluster. We look at the left cluster over here, and we look at all the bases, and we see only a single base, 2. We look at the right cluster, and we only see a single base, 3. So we have a base 2 cluster here, base 3 cluster here. There are no clusters with mixed bases. So again, you notice that there are 2 clusters, and the common bases are 2 and 3. And we're going to use all 3 laws concurrently or simultaneously in order to execute the problem. But we're going to be using these three laws one cluster at a time. When you look at the first cluster, the only base involved is base 2. So we're going to collect all the exponents for base 2. We pick up a 2.2, which is 4, drop it in, a 4.2, which is 8, drop it in. We get a 1.2, which is 2, on the bottom becomes minus 2 on top, and 3.1, which is 3, on the bottom becomes minus 3 on top. Then we hit the separator, which is a plus sign. Could have been a minus sign. So we do a plus, and then of course the second cluster over here only involves base 3. And now we're going to scan for base 3 exponents. We pick up a 2 there, drop it in, a 2.2, which is 4, drop it in, and 3.2, which is 6, drop it in. 3 is in the denominator, therefore it becomes minus 3. 2.4 is 8, in the denominator becomes minus 8 upstairs. Okay, so essentially when we're bringing up exponents, what we're doing is subtracting the exponents. So we continue. Again, we have a simple integer string. We get a 12 minus 5. And a simple integer string over here, we get a 12 minus 11. So 12 minus 5 is 7. So we get 2 to the power 7. And 12 minus 11 is 1. We get plus 3 to the power 1. 2 to the power 7 easily evaluates to 128. And of course, 3 to the power 1 is 3. At the end, you just add, and we get 131. And that's the final answer. Okay, so this 2 cluster mess up here was finally simplified to 131. So let's see what's in store for us on the next slide. Part D over here is called the Distributive Product Law. So we have another exponent law to deal with. The Distributive Product Law, which I abbreviate as DPL, goes like this. If you have a set of brackets and inside the brackets you see 2 different bases and you see a single exponent on the outside, that exponent actually distributes to each base. Why is that true? Suppose C over here were 3. That really means that we have AB written 3 times side by side. Again, suppose the exponent is 3. That would mean that the frequency is 3 for A dot B. So we have A dot B dot A dot B dot A dot B. How many A's are there? There are 3 A's. How many B's are there? There are 3 B's. And therefore, for a general C, this becomes A to the power C dot B to the power C. In other words, the C distributes to both the A and the B, and that's called the Distributive Product Law for exponents. Let's look at some examples that might clarify. Example 1, you've got bracket 2.3 all to the power 3. The bases are 2 and 3, and the exponent is 3. So if we distribute this 3 to each base, we wind up getting 2 to the power 3 dot 3 to the power 3. 2 to the power 3 is 8. 3 to the power 3 is 27. And then at the end, 8.27 is 216. Example 2, we have bracket 3 to the power 2 dot 5 to the power 2 all to the power 3. Now we're going to be using not only the distributive product law, but we're going to be using the power of a power law simultaneously. So the 3 distributes to 3 squared and it distributes to 5 squared. Doing it simultaneously, we get 3 to the power 2 dot 3, which is 6. And we get 5 to the power 2 dot 3, which is 6 as well. And then 3 to the power 6 evaluates to 729. Again, you can do that on your calculator if you want. And 5 to the power 6 evaluates to 15625. And then finally, this product, certainly you want to do this on the calculator, evaluates to 11390625. And the problem is done. The distributive product law also works with fractional bases. Over here we've got base of 1/2 multiplied by a base of 5 over 3. And then we can distribute the exponent. So we get equals 1/2 to the power of 3 dot 5/3 to the power of 3. And then, of course, you can evaluate 1/2 to the power of 3 as 1/8. And then 5/3 to the power of 3. You can multiply that out. I believe you get a 125/27. And then you can multiply that out, etc., etc. I'll leave that for you to do. Okay. Let's go on to the next slide. So we're looking at Q2 over here, and we're going to be using product sum law, quotient difference law, and power over power law. And possibly the distributive law, probably in the next question. I'm not sure because I can't remember. But if you look at this expression over here, consists of a single cluster because there's a dot there, dot there, dot there. So we have a product on top, product on the bottom. That constitutes a single cluster. If we look at that carefully, the common bases are 2 and 3. And again, we're going to be using all three laws to do this. We'll start off with base 2. We'll scan numerator and denominator for base 2 exponents. We pick up 2.2, which is 4, and then 3.2, which is 6, and then 2.4, which is 8, becomes -8. And then we look for base 3 exponents, and we pick up a 4.3, which is 12, and on the bottom 2.4, which is 8, becomes -8. So again, we have a simple integer string here, simple string here. We're going to evaluate each string. We get 2 to the power of 10 minus 8, and we get 3 to the power of 4, and then 2 to the power of 2, dot 3 to the power of 4 is 4.81, which evaluates to 324. So let's go on to another problem. And essentially what I've done over here is I've summarized all the exponent laws. So we're going to go through them in sequence. We have the product sum law, a to the power b dot a to the power c is a to the power b plus c. So the product becomes a sum of exponents, provided that you have a common base. The quotient difference law, QDL, says that a to the power b over a to the power c is equal to a to the power b minus c, provided you have a common base again. The power of a power law, POPL, says that bracket a to the power b all to the power c becomes a to the power b dot c. Okay, so when you have a power and then you have an exponent on the outside, it becomes a product law for exponents. Okay, so you multiply the exponents together. Distributive Product Law, DPL, we've already seen that. We get bracket a dot b all to the power c. The c distributes to both the a and the b, and we get a to the power c dot b to the power c. And then we have a distributive quotient law, which is the counterpart to DPL. If we have bracket a over b to the power c, the a distributes to both the a and the b, and we get a to the power c over b to the power c. And then we continue these laws on the next page. The reciprocal law we haven't seen yet. It says that 1 over a to the power b, which is essentially the reciprocal of a to the power b, is identically equal to a to the power minus b. So whenever you have a power in the denominator with a 1 on top, what you do is upshift. You can upshift the whole power, and it becomes a to the power negative b. So there are two different ways of writing. You can either write 1 over a to the power b, but what this really means is that you have a to the power minus b. Okay? So you can either upshift and change the sign of the exponent, or you can downshift and change the sign of the exponent. Again, you can either upshift or downshift. This particular law over here, using negative exponents, is particularly useful when dealing with calculus problems. Okay, I know that's way beyond you right now, but that's okay. You'll be seeing that a lot in the future. Let's look at the flip chain sign law. Flip chain sign law. I call it FCSL. It says that if you have a fraction a over b all to the power negative c, the negative sign says flip me, so you flip the fraction and you change the sign. So again, a over b all to the power c, you flip the fraction, change the sign. Basic laws. These are laws you should know off the top of your head. A to the power 0 is identically equal to 1. A to the power 1 is identically equal to a. And a to the power negative 1 is identically equal to 1 over a. Again, this is a special case of the reciprocal law up here when b is equal to 1. These laws are all fine and dandy provided a is not equal to 0. So whenever you have a denominator of 0, we've mentioned this before, the resulting expression is undefined. Okay, also a to the power 0 is undefined. 0 to the power 1 is certainly 0, it's defined, but 0 to the power negative 1, which is 1 over 0, is undefined. So we'll try to avoid those cases at all costs. And then the last law that I discuss is a law which takes us from radicals to exponents, particularly useful in calculus. There are essentially two little laws over here. This is a special case of the second one. If you have square root of a to the power b, we have a radical. There's really an imaginary 2 on the outside. And this becomes a to the power b over 2. So that imaginary 2 on the outside, which is not normally written, becomes a to the power b over 2. This is the way we convert radicals to equivalent expressions with rational exponents. Okay, so the square root of a to the power b is identically equal to a to the power b over 2. And the cth root of a to the power b likewise is equal to a to the power b over c. So whatever appears outside the radical is actually in the denominator of the fraction that you see in the exponent. What's understood over here is a 2, so this b becomes b over 2. Over here, we have a c explicitly, so this becomes a to the power b over c. Very useful laws, because it's much easier dealing with rational exponents, aka fractional exponents, than it is dealing with radicals. Much easier to use exponent laws with rational exponents when you convert radicals to rational exponents than it is dealing with the radicals themselves. Okay, dealing with radicals is an unwieldy task, whereas dealing with rational exponents is fairly straightforward, no problems at all. Okay, so I think I'm going to do an over and out for this video. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like and subscribe to our channel. If not, please tell us how to improve it. Over and out for MathLab Tutorials in Toronto.